Good morning, and welcome to another webinar in the Industrial Heating Equipment Association series on sustainability and decarbonization. I'm Ann Goyer, IHEA's Executive Vice President, and on behalf of the association, thank you for joining us in IHEA's largest sustainability webinar to date. We're excited to continue this series on such an important topic. I'd also like to announce that IHEA is launching a 2024 Industrial Heating Decarbonization Summit this fall. It will be held on October 28th to 30th in Indianapolis, Indiana. The purpose of the summit is to forge a sustainable path to decarbonization for all companies in our industry. We are finalizing the program now and will have the registration open very soon. Be on the lookout for email announcements, and all the details will be posted on IHEA's website, www.ihea.org. Before I get started, I'd like to remind everyone that all attendees are on mute. If you have a question along the way, please type the question into the question panel and the speaker will address the questions at the end of the webinar. All attendees will receive a brief survey after the webinar. It will take just a few minutes to reply. We appreciate your feedback as IHEA continues this critical initiative for the industrial process heating industry. One last announcement, this webinar is being recorded and it will be available in the sustainability section of the IHEA website within the next few days. You'll be receiving an email once that link is available. Now it gives me great pleasure to introduce the presenter for today's webinar titled Hydrogen Basics. Brian Kelly is the Applications Engineering Manager for Honeywell Thermal Solutions. He holds a bachelor degree in aerospace engineering from the Pennsylvania State University. He has close to 30 years of experience in the industrial thermal processing industry, and he is past president of IHEA as well as chairperson of IHEA's Educational Committee and the Combustion Seminar. He has authored numerous articles for the process heating industry in various publications. Brian, it's all yours.
Thank you very much, Ann. Welcome everybody to our next series in the webinar here. What we're going to do today is talk a little bit about hydrogen basics. Mr. Jason Safars of Carl Dung's a few months ago went through some basics as it relates to control components, some basics of hydrogen, and some of that. What we're going to do today is again review some of those basic properties of hydrogen and a general comparison to natural gas and its combustion characteristics. And really what we'll do is we'll review some burner, as we related, us burner guys, how hydrogen affects certain different burners, how it relates to burner design, flame detection, with blending and different ratios of hydrogen to natural gas, how that affects air-fuel ratio, stoichiometry, as well as safety and control components. Hydrogen being a carbon-free fuel, we'll talk about that, and we'll look at the reduction possibilities when we're looking at firing hydrogen and hydrogen blends, as well as the effect on other emissions as well. And then we'll finish up by discussing the different types, really colors and sources of hydrogen. So when we talk about hydrogen, and that's the potential being carbon-free, right? If we look at the basics, and I did not put the nitrogen in the air, but as we look at the chemistry of it, when we have natural gas, which is basically methane, CH4, we combine that with oxygen and we get CO2, water vapor, and energy out of that. When we look and look at hydrogen, you'll see there's no carbon in hydrogen. So we really just take that hydrogen, it combines with the oxygen, and we produce water vapor and energy. So there's that potential. When we look at that hydrogen possibly being produced with a renewable energy source, that hydrogen as an energy carrier results in a CO2 neutral energy form. So there's a lot of talk, as we have throughout this series discussed, of investigating ways to decarbonize and reduce our carbon footprint on our thermal processes. So a little bit about hydrogen properties and combustion characteristics. The hydrogen atom is the lightest and smallest element in that periodic table. So there we've got one. So it's 8 times lighter than natural gas. Hydrogen is colorless, odorless, and tasteless. So why is that important? Well, if we compare it to natural gas, it's a smaller molecule. So it would have more possibilities of leakage. Certainly that lighter atom is going to affect the characteristics of it flowing through pipes, valves, things of that nature. So why is that important? Well, that's when most of us combustion component manufacturers are testing hydrogen on our burners. We're internally certifying it, that all our control components, our shutoff valves, all those components are suitable for a 100% hydrogen, so that we have a, I'll say sustainable, but we have a system that is safe to operate and has no issues going forward with meeting all those safety components that we have on our checklist when we're building a combustion system or a thermal process solution. Hydrogen requires 15 times lower spark energy to ignite the natural gas. So along with that, it's got an extremely wide flammability range. So from a combustion standpoint, it's very easy to light. That wide flammability range, where if you'll see that little green bar next to the hydrogen, natural gas and air has from our lower to upper explosive limit about 5 to 15, where you'll see with hydrogen is about 4 to 75%. So hydrogen is very easy to light. So if we have some fuels that are a little diluted, but there's some hydrogen in there from a combustion standpoint, that's helping us maintain that combustion within the burner itself. One thing to note though is that flame burns depending on the design of the burner and how it's introduced 5 to 8 times faster than natural gas, and it results in a higher flame temperature, about 400 or 500 degrees. So as we look at this picture here, a burner stabilized flame in this vessel is it's what we call a nozzle mix burner. The fuel in the air is delivered to whatever nozzle mixing device, and that flame stays stable on that burner stabilization device, that nozzle. With hydrogen, you have a greater propensity to flash back. Because that flame speed is so much higher, it has the potential, if there's air mixed with that fuel, and we'll talk about some burner types, it has more of a chance of flashing back. So that's a safety design, a safety concern when, I would say safety, but it's a burner concern that we are flashing back. The heating value of pure hydrogen is about 3 to 3.5 times lower by volume than most commercial natural gases, so approximately 325 BTUs per cubic foot. So that just means equivalency, we're going to need about 3 to 3.5 times more volume of hydrogen to get our equivalent capacity through the burner when we're burning natural gas. And we'll talk about how that affects the stoichiometry and the pressure required at the burner in a couple slides here. So when we look at burner challenges and firing hydrogen, so if we look at, as we said, the flame temperature is about 400 to 500 degrees hotter than natural gas. So on our left over here, when we have the possibility of overheating burner parts, that flame stability, that flashback possibility. So those parameters involve flame speed, the flammability limits that we just talked about, that flame temperature, and really it goes to burner design. Again, here, our little image here is a natural gas flame versus a hydrogen flame that has, when that flame speed, when the pressures in a burner get lower, you've got that flame speed that has the availability of having that burner flash back. So what are our solutions from a burner side of it? We actually have, there's burners that require no modifications to burn either natural gas or hydrogen. Or we look at slight modifications and material changes to make sure that the increased flame temperature won't wear out burner parts. Different, if something's cast iron, we go to stainless. We look at slight modifications of a nozzle to make sure that we're accommodating that higher flame speed and we don't have issues in the future, because we want our burners to last just as long on hydrogen as they last on natural gas. Or you've got a solution is to limit the amount of hydrogen in there, but that also limits your availability to decrease your carbon, right? And there are more difficult, when we look at the stability, there's more difficult burners. I'll say more difficult. The design of a burner, something that involves a high spin or premix, you can imagine would be much harder to operate on hydrogen because that flame speed, especially in a premix, that's an explosive mixture. And premix type burners are very limited in their turn down. So premixes does not play well with hydrogen, but on some burners are require more extensive modifications or redesign to make sure that we have the performance that we are delivering on natural gas, and that same performance and capability when firing percentages or up to 100% hydrogen. Ignition stop behavior. What we mean by that is that the effects causing flashbacks. And what I mean by that is when we start and stop a burner on natural gas, that flammability range that we talked about is pretty narrow compared to hydrogen. So as we said, hydrogen is very easy to light. But when we start and stop a burner, depending on we have to adapt that light off capacity sometimes. Purge with inert gases. What we do when we start and stop burners, we either, depending on the situation you're in, that you want to burn natural gas or hydrogen, we either purge with an inert gas like nitrogen. You can stop with natural gas. We look at the shutoff valve placement to make sure that there's not a whole lot of volume in the gas pipe from the last shutoff valve to the burner. Possibly check valves. And we do that because if there's hydrogen in that line and you've got air, you can have that air and hydrogen mix a little bit together depending on the orientation of your piping. And when you start that burner on pure hydrogen, you've stopped it and you go back to start, you can have a small or sometimes big pops when you go to light the burner. Not many people like their system popping. Big bangs don't go well in plants. So when we're looking at that system design, depending on capacity and the size of the piping and the burner, we look at possible solutions to make sure that start, stop, and ignition behavior is very similar to what you would experience on natural gas or any other fuel. Flame sensing. So when we look at flame sensing, scanners or flame rods, ionization, we start getting above 80 to 90% hydrogen in a mixture of natural gas, and that flame rod will no longer have an adequate signal to keep your flame safety locked in, just because of the reduction in carbon, and you'll see what the flame looks like. There's just that lack of carbon. So pretty much UV scanners, we've tested them, and up to 100% firing hydrogen is no problem. And what we've seen in some of the burner designs that Honeywell has is that when, depending on the mixing and the design of that burner, we've seen, because of that higher flame speed of hydrogen, we've had some resonance effects in some burners. So that's combustion dynamics involved, the mixing principle. So really the solutions there are, again, some modification of parts and internals, also limiting hydrogen. We've seen that, but again, really the challenge or the goal, I should say, is to be able to run those systems on 100% hydrogen to offer that capability of eliminating that CO2 or that carbon from your products of combustion. And with looking at flame properties, the geometry, the radiation, pretty much those parameters are involved are all combustion parameters. But our experience of many of the burners we've tested in our labs is there's no significant difference in flame geometry. At some mixtures, you'll see a slight, in some burners, you'll see a slight decrease in flame length. In some mixtures of hydrogen, and we've got a little video coming up probably in the next slide to show what the differences in flame appearance. You'll see here on the left is one of our total air duct burners. You'll see 100% natural gas, that usual blue flame, and then a very different looking flame on 100% hydrogen. It's a little more opaque, and in a hot furnace you could barely see it. That goes for natural gas as well. So but the same challenges years and years ago that oil was a preferred or the fuel available to use in our combustion systems when we switch to natural gas, doesn't have as much radiation coming from the flame as oil. So that changed some people's design. Hydrogen is a little less radiation than natural gas. So it's just things that will be considered down the road in some of our furnace and oven designs that we have with our customers out there. So what we see here is a high velocity burner burning 100% natural gas. In a few seconds here, we'll start adding the hydrogen, but it's your typical high velocity blue pencil-like flame coming out of a high velocity burner. You'll see up in the upper left there, our hydrogen's increasing a percentage at a time pretty fast. Up, you can see at 25%, there's really no change noted. Even at 50%, you might start seeing that flame come back a little bit, but it's still blue. That carbon's still in there. And until we start getting up about 75 to 80%, that's when you'll start seeing your flame change in color. And then about 90%, we go to that very opaque orange-looking flame. So you can see that it's a little more opaque. Certainly the radiation's decreased. But in a lot of our systems these days with high velocity burners for ceramics and heat treating, we depend on that high velocity, which you'll get with hydrogen as well. There's no change there in the velocity out of the burner. Actually, with an increased flame temperature, you might actually get a little more velocity burning with 100% or some percentages of hydrogen. So we had talked about, or I mentioned the pressure requirements and the combustion air requirements. It's a little bit of an eye chart here, so I'll step through it, try to step through it slowly. The required pressure at the burner, if there's not a great deal of modification to the burner, will be higher with hydrogen compared to natural gas to achieve that same capacity, right? So we need that about 3 to 3.5 times more volume. What you'll see on the chart here is over the fuel pressure is our dashed red line, and then the fuel flow is our purple line here. And these are reference values to natural gas. So at 0, our x-axis down here is the hydrogen content in a natural gas blend, so 0 to 100%. And then our left axis here is the relative fuel flow and pressure of air, and then fuel flow and pressure on the right. So when we start increasing our percentage of hydrogen in our natural gas, you'll see logically our fuel flow needs to increase to maintain that capacity on natural gas. So at 50%, even to 100, there's our 3 to 3.5 times fuel flow required. And you'll see a little phenomenon here with the fuel pressure is at about 80–85%. Mix of hydrogen and natural gas is the maximum fuel pressure we need. And then it actually decreases a little bit once we get to 100% hydrogen. And that's because of the density of the fuel. And it's a Wobbe index, right? It's the density and the calorific value of the mix that go and see that little drop in fuel pressure. So it's something to note, and we'll talk about that in a little bit. When we start looking at the combustion air requirements, or the ratio stoichiometry of the required air volume through the burner is actually lower with hydrogen than for natural gas to achieve that same capacity. And what we mean by that is if you look at our light blue line here is the stoichiometry air for the same heating value of natural gas. And then our dashed black line is the air pressure. So as we start increasing that hydrogen content, the required air for stoichiometric firing, that was a tough one for me this morning, it gets lower. So what you'll see is that at 100% hydrogen, your air requirement is about 85% versus natural gas for that same thermal input. And then being square root law, the air pressure obviously is lower to deliver that volume of air. So when we start talking burner control firing hydrogen or blends, when firing 100% hydrogen, it's very similar control methods can be used with hydrogen as with natural gas, whether you're talking air and gas control valves and some type of, whether it's linkage, parallel positioning system to control those burners, ratio regulators, those type of components have been tested to make sure they're suitable on hydrogen. And they'll control, obviously we have to look at volume coming through the device, but with that lower density, the increase in pressure drop isn't as severe as you would think requiring more than 3 times the full volume, or the volume versus natural gas. Firing a fixed natural gas and hydrogen blend, same thing, similar control methods to natural gas. When we look at if you would actually have, this makes control very more difficult when you have a variable blend, hydrogen blend in your natural gas while the burner's operating. Makes it, that variable blend will have an effect on the possible maximum capacity of the system and the air fuel ratio. So when we look at that possibility, is what's the critical factors that are going to drive the complexity of the system, especially controlling, is it more critical to maintain an air fuel ratio, excess air, to maintain the maximum system capacity, or do you need to maintain both? Because the more, obviously, the more complex you get, the more complex your system will be to maintain those factors. And again, what we look at, if you need to maintain the same capacity, how does that affect the other factors in the system? So what the requirements for flows and pressures, the air factor or excess air, when we start increasing the hydrogen in the natural gas blend, and what you'll see here is our bottom line here is that capacity. We're holding the capacity of the burner, the system. So what happens is when we hold that capacity, you'll see that air factor, that percentage excess air, goes up as we have increasing hydrogen. As we just mentioned, the stoichiometric requirement for air is less with hydrogen. So when we maintain the same capacity and the air is not changed, our excess air goes up in the system. And that's really what this chart is showing here, is that percentage excess air is going to increase if we maintain that same capacity, and no other adjustments in the system are being introduced to hold that excess air. This should be no problem if we look and discuss low temperature applications, line burners, duct burners, things of that nature. Generally, excess air is not a problem because those systems are already operating at extremely high excess air oxygen levels in the system to dry, to do other things that are a couple hundred degrees Fahrenheit. When that excess air is important, this type of system really is going to not be a good solution, right? And we kind of list here, this is ideal for raw gas burners, right? It's like just maintaining your input to get to a certain set point in your air temperature when you're heating, air heating. When we look at maintaining that same air fuel ratio, what you'll see is we now are maintaining that air factor, that excess air. So what happens here are when we held that capacity constant, our excess air went up. When we hold that excess air constant, our capacity will go up. Because we're holding that X percent of excess air. The capacity is not checked, not adjusted with that fixed air. Again, and this is we can't get into it today, but it comes back to the system design, right? It is much easier to design a system when we have fixed hydrogen and natural gas blends than something that can vary. This type of control is okay if it's compensated by the capacity control of the installation. So in most installations, a thermocouple is driving control. So if the capacity rises, the maximum capacity in the burner rises a little bit, it's just going to maybe heat things up a little quicker, and you'd have to adjust your control system to do that. This has limited impact on turn down, but this type of thing for high temperature applications and sensitive burners, and a lot of our high temperature applications that deal with alloys, metals, even ceramics, we want to generally have a repeatable air fuel ratio because excess oxygen can affect some of the products that we heat in a lot of the processes that we deal with in our industry. So that's all the talk, right? CO2 reduction with hydrogen. So 100% hydrogen combustion, no carbon in your fuel, so your resulting CO2 should be zero. When we look at that CO2 reduction with blending hydrogen and natural gas, obviously we're displacing that CH4, that methane in that natural gas with hydrogen or a carbon-free fuel. But when we have a chart that shows the CO2 reduction as we start increasing that percentage of hydrogen in the mixture, but it's not a one-to-one or a direct correlation to the amount of CO2 reduction you're going to get with the percentage of hydrogen in that natural gas hydrogen blend. So this results in the hydrogen's lowering the heating value of that mixture, and with its low density, you'll see that in the next slide, to really realize a 50% reduction in CO2, you're going to need almost 80% hydrogen in your hydrogen natural gas blend. So what this chart shows is it's not one-to-one, right? Just because we have 50% by volume, and this is the key, right? Because it's a lower heating value, but it's also much lighter. So by volume, if we have a 50% hydrogen natural gas mix, our CO2 reduction is a little over about 21 to 22%. So you'll see where looking at that 50% CO2 reduction takes you to about 78%, 80% hydrogen, your natural gas. So that's something to be aware of when you're looking at, because there's a lot of discussion of blending, injecting hydrogen into natural gas grids up to like 17 or 20%. But that's going to get you 20% hydrogen blend is going to get you about 6% CO2 reduction, which, hey, everything we can do to reduce CO2 is a good thing. But it's just something to be aware of, the nature of the hydrogen, because if it's lower heating value and that lower density, so by a volume, it's going to take a bit of hydrogen to get more significant reduction in your CO2 output. So we talk other burner emissions. CO2 is important, but for a long time of our industry, there's been legislated NOx requirements for different applications, right? California being one of the most stringent, but we're seeing more and more requests for lower and lower NOx burners. Impact of hydrogen on NOx. In our traditional burners that we're doing testing on now, we do see volumetric, we see NOx levels increasing as that hydrogen percentage increases in the gas mixtures. And that's resulting pretty much from that increase in flame temperature. There's no way of getting around those physics. But something to note is that by this volumetric reference and measurement, most plants would have a tons per year, some type of measurement. ppm is a very convenient way of measuring NOx. CO2 is generally in percentages, your CO, but it can be misleading because of that change in the volume of the products of combustion and other corrections when we're looking at firing hydrogen. So the volumetric comparison we say should be avoided, and more of a mass per unit energy is recommended. Compare NOx from natural gas versus hydrogen combustion, and we'll show you an example of that, because most burners with turn down, that volumetric measurement of especially NOx generally increases in most burners. And as I had said before, the techniques we've used for many, many years to reduce NOx, and that's the use of excess air or spin in a burner or some premix, don't agree well with hydrogen because of that higher flame speed. So it's a challenge to us burner manufacturers when we start looking and talking the next generation burners that can be fuel flexible and be low NOx, whatever fuel we're burning, right? Again, like I just said, I'm ahead of myself. So that burner mixing design definitely influences the hydrogen impact on NOx. As I had said, some burner designs will not work or may be very challenging that What we've seen that NOx increase as we test our different blends of hydrogen, but above 70%, we see the notable shift increase in NOx starting to happen. And resulting by volume, that's probably when we're starting to see our most significant shift in flame temperature as well. As I said, that volumetric measurement should be avoided. And then what about CO, right? If we have a pure hydrogen fuel going through a burner, there should be no CO, so there's no carbon. And just a few things to try to understand when I'm talking about that volumetric level and the changes. Obviously, that ppm level increases because of our flame temperature, but also when we talk volumetric versus that per unit mass energy, say pounds per million BTUs. What this is showing us is that stoichiometric error. I'm having trouble with that this morning. For that same heating value, for that same input with natural gas, you'll see we're down about that 85%. So we now have less volume of products of combustion, and then we also have less flue gases, obviously, is our purple line there. When we look at that evolution of the air and that CO2 in the wet flue gases is from zero, there's our zero CO2 and the resulting percentages as we increase that hydrogen in that natural gas mix. And then also to be noted, obviously, we are now with the reduction in CO2 and the introduction of a pure H2 source, we're combining with the oxygen. So we have some more moisture in the flue gases as well. And many of our customers are testing these blends and even pure hydrogen and with their materials that they're heating to make sure that in a situation where they would have the opportunity to burn hydrogen, that they're not going to see any product quality differences. So we've got that reduced flue gas flow with that increased hydrogen blend. So just to put some numbers to it, when we're looking at the NOx generated, if it's 50 ppm corrected to 3% oxygen, that correlates to about 0.06 pounds per million BTU. If we look at that same volumetric level, that 50 ppm at 3% O2 actually correlates to 0.041 pounds per million when we're looking at combusting pure hydrogen. That is a combination of the heating value of the fuel, its density, but also mainly that reduction in the flue gas. So it's important to note that to be in the same pounds per million or that mass per energy basis with hydrogen as with natural gas, that conversion of that 0.06 pounds per million actually correlates to about 73 ppm corrected to 3% for pure hydrogen firing. So it's something to be noted, and it may be something in the future that the environmental agencies are going to have to recognize that there's a difference here when you're burning hydrogen or even percentages of hydrogen, and something's been guaranteed on an emissions level on a parts per million or a volumetric basis, and to go back to something that would be more universal in terms of that mass per energy basis, that pounds per million, to make sure that you're in compliance, because this relates to the pounds per million, that's that energy, and this is a direct weight of the CO2 that's going in the atmosphere. So it makes a difference. So as we talk about hydrogen, where do we get it, right? And that's a lot of discussion, is where does it come from? And this hydrogen color wheel, there used to be like blue, green, and gray. Now there's all kinds. When we talk about the majority of the hydrogen that's available right now versus what white is naturally occurring hydrogen, that gray is natural gas. It's derived from natural gas. 90+% of our hydrogen that's available on the market today is gray hydrogen, and that's generated from steam methane reforming. Most of it's in your oil and gas, your refineries, and it's by far the most common method today. And it's a byproduct, right? They've been using hydrogen in refineries as fuels because it's a byproduct. So they utilize it to heat many of their processes. When we consider blue hydrogen is gray hydrogen with the CO2 captured or sequestered somewhere to minimize and to eliminate that CO2. And green hydrogen is what you'll most commonly see made reference to when we talked about that renewable energy source. Green hydrogen is made by electrolysis using electricity from those renewable sources. So we split the water into hydrogen and oxygen without emitting any CO2. So that is a renewable or a carbon-free hydrogen source. What you'll see is the purple, pink, and reds. That's electrolysis. It's a production process similar to the green hydrogen, but powered by nuclear energy. Your yellow refers to hydrogen made from solar. And then your gold is by fermenting microbes found in depleted oil wells. So the process relies on CO2 capture for carbon neutrality. Your brown and your blacks, that's making hydrogen using either coal or oil. So it releases high amounts of CO2. So then you have to look at some type of capture technology there. So just be familiar with a lot of the colors, but really the main ones that get discussed most frequently today are the gray, the blue, and the green hydrogen. But as people look at being able to produce hydrogen and have it available to be an energy source, that carbon-free energy source, you'll see more and more processes and probably more colors that are identifying where that hydrogen and how that hydrogen is being produced, because you're going to have a combination of technologies to be able to do that when you're not in a pure electrolysis, electrolyzers. You're going to have to refer to some type of carbon capture, some type of technology to be able to remove that CO2 from that carbon to be carbon neutral. And there, we look at timelines 2020 to 2030 we'll start looking at that gray hydrogen, blue hydrogen, and then underground storage or some kind of carbon capture, and then eventually getting to your green hydrogen. All of these have a cost as well, right? Gray hydrogen is going to be your cheapest because as you start looking at removing the CO2 from the existing gray hydrogen or green hydrogen, the power is going to be more expensive. So over time, just like everything else, some economies of scale, the ability to mass produce this fuel will have an effect on its price. And as we look at those renewable energy sources too, I had mentioned that the most economic way, right, would be distribute hydrogen is maybe to mix it in existing natural gas grids. We have to look at the grids. Does the substructure exist? Some studies saying that blending up to that 17 or 20% is acceptable without changes to the distribution network, and maybe minimal changes to appliances, say household furnaces, stoves, maybe commercial boilers. But as I said, there's a lot of burners that have been developed out there that use techniques that may not agree with hydrogen. I can tell you that some of the burners that Honeywell makes right now in their existing format, there are a few that are not. We do not endorse any hydrogen being mixed because of some of the overheating that we can get into. What we'll see in the future, maybe local small scale hydrogen distribution and may go up to 100%. Longer term, higher levels of hydrogen will be targeted. This is going to take time. And on-site production. There's going to be some people there. I mean, there's plenty of companies that have electrolyzers, right? And they're getting larger and larger. Then it's going to be what's the energy source and what's required for your particular production facility. What type of volume do we have to produce to be able to run that facility consistently on 100% hydrogen? Last year, it was a bipartisan infrastructure bill. October last year, $7 billion was released for the production or the future of clean hydrogen, right? This is to launch 7 regional clean hydrogen hubs across the nation. Those locations are, you've got the Appalachian hub, that's in that West Virginia, Ohio, Pennsylvania area, California, the Gulf Coast region, what they call the Heartland, which is your Minnesota, North Dakota, South Dakota. The Mid-Atlantic is your Pennsylvania, Delaware, New Jersey. The Midwest, your Illinois, Indiana, Michigan areas, and then the Pacific Northwest, Washington, Oregon, Montana. All these are targeting to be hubs and to have considerable capabilities of producing and then be able to distribute the hydrogen. And I want to thank you. I hope this has been educational for you all. I'm sure there's some questions, and I will reiterate, we are having this fall, October 28th to 30th, and IHEA Industrial Heating Decarbonization Summit in Indianapolis to cover pretty much all areas that are related to decarbonization. So it promises to be a very exciting and very educational event.
Thanks, Brian. A lot of great information, a terrific overview of hydrogen for everybody to get started. If there are any questions, please type them in the question panel now, and we'll be sure, we'll ask Brian to reiterate some of those statements there. But in the meantime, I just wanted to thank everybody for joining us today for this webinar. I also want to remind everybody there is a sustainability tab on the menu bar of the IHEA website, and there are several other resources available there. And then also, again, the summit information will be posted on the website as soon as that program is confirmed, which will be very shortly here. We also will be sending a link to a survey, and we would appreciate your feedback. It should be available as soon as we get off the webinar call here. Are there any questions for Brian before we close out today? Okay, the question that just came through is there is going to be a recording of the webinar. Yes, as soon as we have that available, we will send that out through an email link. So all of our webinars in this series are posted on the IHEA website in the store, so you can find those there. There is another question here. Does Honeywell have case studies available for hydrogen applications?
Yeah, if you go on the Honeywell website and we can share that. But there's some case studies, there's some white papers on many of the topics, especially on burning hydrogen. So yeah, we've got those resources.
Perfect. Brian, another one here. Are safety standards ready for industrial use of hydrogen?
That's a very good question. I think Jason covered that a couple months ago. So in our fervor to decarbonize, the safety and standards, there are NFPA standards on hydrogen, NFPA 2 and 54. Our normal NFPA 86 and 87s have not caught up. They identify hydrogen as a fuel in the latest revision, but they also refer to the NFPA 2 and 54 standards. So there are some standards to cover that. From a burner combustion system manufacturing standpoint, some of those aren't in, some of those standards refer to high and low pressure. Jason had mentioned the subject of hydrogen embrittlement, which in your refinery type installations where they are transporting fuels at 5 to 1,000 pounds, we're dealing with a couple pounds of pressure coming into our system. So in those lower temperatures and pressures, hydrogen embrittlement, at least for the foreseeable future, isn't a problem in our type of systems. So the standards will need to catch up. There's enough out there that we've been doing this for, we've been burning hydrogen for 100+ years, right? Coke oven gas, town gas, high up, very, very high percentage of hydrogen. So this is nothing new, but it's going to take a little time for some of our normal standards to catch up, but they'll get there.
Okay. All right, any further questions? Okay, yes. For larger applications, do you foresee the delivery infrastructure being ready to accommodate, or will on-site generation likely be the preferred means?
That's a very good question, and who knows, right? That infrastructure for hydrogen is going to have to be built. There's no way around it. This is not something that's going to happen in the next couple years, right? I think a lot of the customers that we talk to about this want to be hydrogen capable or ready. So when they're looking at new systems, they want the system to be able to be switched over, have capability of up to 100% hydrogen, but knowing that things today, they're going to be operating on natural gas. We've delivered a number of systems that we've started up on both natural gas and hydrogen. They brought in tube trailers to make sure that the system is capable, and they go back to natural gas until they can get that hydrogen reliably delivered. And just looking at the technologies, be ready, but look at your burner technologies as well to make sure that you're burning the natural gas as most efficiently as well. So looking at whether it's recuperation, air fuel ratio control, those are methods that you can reduce your carbon today without even switching fuels.
It's a good time to take a look at it all and get prepared, right?
Yep.
Yeah, great. Okay. Anything else for Brian? Or Brian, do you have any final comments for us?
No, I just hope it's an ever changing landscape. So we see a lot of inquiries these days for syngases that they're producing with trying to produce hydrogen. So it's keeping the burner guys on their toes. So it's an exciting time.
Great. We did have one more question here. Can you talk about white hydrogen?
I don't think I'm familiar with light hydrogen.
White as in the color?
White hydrogen.
Oh.
White hydrogen is
White.
it's what's coming out of the ground, right? So it's naturally produced, naturally occurring in nature.
Yeah. All right. Well, I think that'll wrap it up for today. I just want to thank everyone again for your attention and remind you, you will get an email for the survey, but also in a couple of days, you will get the email once our recording is available. So stay tuned to the IHEA website, and we look forward to doing this again next month, but have a great afternoon, everybody. Thank you.
Thank you, everyone.